The circuit shown in figure P 4.5 is a model for a battery charger. Here VI is a 6 volt peak sine wave, D1 and D2 are ideal diodes, I is a 60 milliamp current source, and B is a 3 volt battery. Sketch and label the waveform of the battery current IB, what is its peak value, and what is its average value. Alright, so the way I approach these problems is that I assume that like both of the diodes are on, or one of the diodes is on, and then I look at what the node voltages will be along the circuit, and then what those voltages how those measured voltages correspond to the properties of an ideal diode. Okay, so it's the way. I mean, it's kind of like a new way of looking at circuits after all the KCL, KVL, and phasor analyses you've done. It's just a different way of like analyzing circuits. So we go ahead and assume maybe D2 is on and D1 is on, or both of them, or just like kind of look at it like this. If you want to do it my way, it's like we can assume D2 is on. So we short this, and we'll see that this whole entire node would be at 3 volts, right? And if this whole node were at 3 volts, then when this voltage source is like 1.1 volts, 2 volts, right, up to 3, then this voltage would be smaller than this 3 volt voltage, right? So that would make it conduct in this direction. So that would short this, right? And if it shorts this, then this node now becomes this 1.1, 2 volts up to 3 volts. And so if this is like 1.1 to up to 3 volts, then this voltage is going to be lower than this 3 volts over here. And so this is going to be shut off, right? And that's all okay in terms of like corresponding to the physical current and voltage terminal characteristics of an ideal diode. So basically between the voltages, if the input voltages from 0 up to 3, up here, this whole area, it is going to be D1's going to be on. D1 is going to be on here, and D2 is going to be off. Okay, so that would mean IB is 0. And let's keep looking at this, right? Now let's stick with D1, and now we have, let's say basically like a voltage of, suppose voltage of 3.1 volts here. And if this were 3.1 volts and shorted, this whole entire node would be 3.1 volts. And now this diode would be like, hey, well 3.1 volts is greater than 3 volts, so now IB would conduct forward, that would short it, and this whole node voltage would now become 3 volts. So if this were 3 volts over here, and this were 3.1 volts, or yeah, if this were 3 volts and this were 3.1 volts, this is a higher voltage, so current would not be able to conduct in that direction, because current travels from higher to lower voltage, and that would be in the direction in which ideal diodes don't conduct. So D1 would shut off, and that's totally cool. That's totally okay. That's like not a problem. That's not a problem at all. So then during this higher part, D1 would be off, D2 would be on, right? And then what about when it goes negative? All right, well, let's look at that. Same way we did the first two parts. So I'm doing this on the fly too. So let's say V1's like negative 1.1, negative 2, all right, whatever. And let's say this is on. let's say D2 is on, so this would also be 3 volts. This whole area would be 3 volts. This whole node would be 3 volts. And if this were 3 volts and this were something negative, then current would travel in that direction. And if current traveled in that direction, then this would short. And if this were shorted, then this whole entire node would be whatever these negative voltages are. It would follow this node would be whatever, it would follow this negative voltage. And so this would actually be this voltage, yeah. And if this were 3 volts and this were something like from 0 to -6 volts, then it would not conduct current in that direction. This would be off, and that's totally cool. It would make sense. It'd be like it'd be right. So during this part, yeah, during this whole part, D1 is on and D2 is off, so IB 0. And during this dotted part, D1 is off, D2 is on. So if this were on, this were off, and this current were that was conducting, this current source here was conducting 60 milliamps, then IB would be 60 milliamps. So that's the peak value. What about its average value? We can do an average, you know, like how much time is, you can just do an average. And I know that since this is a sine wave, to get to half of the height, because the sine wave, sine is peak 1 volt, then the y-axis is at 1/2 when you're at pi/6 radians, right? So this would be at pi/6 radians, and then it would be at 1/2 again at, let's see, pi/6, 2, 3, 4, 5, at 5 pi/6 radians, right? And this would be up to 2 pi, or whatever. So you would have current for 4 pi/6 or 2 pi/3 out of 2 pi. That much time divided by 2 pi. So a third of the time you're on, and if you're on a third of the time with 60 milliamps, your average is going to be a third. So the average current would be 1 milliamp, I think. What about the peak value of VI reduced by 10%? What would the peak and average values be? So if we reduce this by 10%, we reduce this by 0.6, so this would be 5.4. The same thing would happen with this turning on and off at 3 volts. The only things that would change are the averages. So we would have to find, instead of pi/6 and 5 pi/6, at what point does a sine wave of 5.4 volts hit 3? Get what I'm saying? So if it were like, right, so I'll just 3 volts. You could probably carry it out from here if you understand what I'm saying, or whatever. But you could divide and then inverse sine if I find t to figure out at what times you hit that point. So let's do that. So inverse sine of that, I get t is equal to 0.589, and that would kind of make sense, right? Give me a second, because I'm doing this on the fly. How close does that line up to like pi/6, right? That's pretty close to pi/6. That makes sense to me. Then we would need this other one. We need this other point. Now when we do that, this is one of those moments in life where like using a real calculator, like even like just not doing it like manually, like you just use it like a graphing software, like this is where it would work. This is where it's, but fuck it, here we are doing like homework, right? How do you do this? I'm gonna go out on a limb here and just use like, right? If from 0 to 0.8 to 0.589 gets you here, then from pi to pi minus 0.589 gets you there. Am I a genius or no? Who knows? Who knows? Let's see. 589. 2.55. About. It's 2.5525. So how about that? Let's run that sign. Times 5.4. Yeah, it's 3. Oh my god, I'm a genius. So that's the times. That's the new times, and so the peak value is still gonna be 60 milliamps. What about the average value? Okay, so how much? All right, what's the difference? Like, right? So what's the delta T between here and here? Let's do 2.55 minus 5.589. That's 1.96. You divide that by the total time from 0 to 2 pi. So if we do delta T over 2 pi, that would get like the fraction. And the delta T would be 2.55 minus whatever, divided by 2 pi. We get some number, it's 0.312, which is pretty close to 0.333, which is that 1/3 from earlier, and multiply that by 60 milliamps, and your average current in this new case would be 18.726 milliamps. Right? Ta-da!